Good morning, my dear students. In today's class, we have the revision. So we are going to explore the few more numericals on the ethane thermodynamics here. As I gave previous class the assignment, it's not that compulsory you have to do all. What all questions already you have done and what is left over, and you feel this is a very good conceptual question, you have to identify. Don't ask me, sir, please do identify good questions. You try to identify the questions which are of the level of advanced, means categorization, because this is what you have to learn. Observation of question also something very important skill which is needed for in exams. That's why I'm giving some bulk of questions there. So anyway, they're based on the topics. So pick up the questions and start thinking them. So I think by tomorrow your everything, the collection, everything should get over. That's what I suggest. Like, okay, today again I'm going to bring few more numericals with a different application. Through numericals only I'm trying to explain concept. There's a best way of revising in a short time of, because in a less time how you can recollect means through numericals only better you revise rather than reading theory again doing numericals. Choice is yours. Read theory then do numericals, or through numericals you can do revision. Let me start the class. Read the question. Okay, no. So initially the piston is somewhere here. V1, you look at the V1 3 liters and V2 2 liters. So definitely I have to show volume of on the left side of gas should be more than that one. Piston is having a mass M. There's everything is insulated. Even look at the piston is also insulated. Now the pressures, you look at P1 4.4 into 10 to power of 5 pascals, here 2.5. So the pressure force here P1A, P2A. P1A is greater than P2A. Okay, now it is the piston is released. So definitely it is released from rest here. So here the gas is present. So helium gas, the same helium gas. Now what to do here now? Say just stick on to the basics here. The net force on the piston is towards right. Then it's going to accelerate. No, let's say this is a fixed here. This is a fixed. The piston is free to move. The partition wall released. It can move without friction. Find the maximum speed acquired by the partition wall. Go back to the like a gas, it comes in contact with the piston. So it's exertive force. So P1 is greater than P2. So therefore it start accelerating towards right. The piston will start accelerating towards right. Then take help of the laws of motion. As it starts moving towards right, what process the gas in the left part will undergo? It will undergo adiabatic process because there's a non-conducting wall. Piston is also non-conducting. And what about here? The chamber is non-conducting and the piston is also non-conducting. So the gas in both the parts will undergo adiabatic process. You can ask one beautiful question to your teacher, like, sir, is it adiabatic? Must be adiabatic? Yes, you can put it. Yes, must be adiabatic. Then is it definitely? I'm going to write equation. Will it be like this only? Need not. The level of questions what we are discussing for adiabatic process means for granted we take it. But what is the adiabatic process? This PV equal to gamma equal to constant is one of the case for adiabatic process. It can be anything, no? If Q0, no heat exchange, then it's adiabatic process. P V to power of gamma is one of the case in adiabatic process. Not like in every adiabatic process, this should be the valid. Since in our syllabus, no, when we say adiabatic process, we just go for P V to power of gamma equal to constant, that one. That's quite natural. But it may change some situations. Now when the speed will be maximum when the net force is 0, How come net force when it is on 0? Because it's going to accelerate as it moves towards right, adiabatic expansion, this is adiabatic compression. So because of adiabatic expansion, this pressure P1 should decrease. This is going to, pressure should increase. At one instant, the net force will be 0. After this moment, the pressure in the right part will become greater than this. It will start undergoing retardation. So somewhere when the net force is 0, then it will have maximum speed. Meanwhile, what is the volume acquired? We'll write it VL and VR symbol. Some symbols will take it. Volume of the gas in the left part and the right part. This will have the maximum speed. We have to calculate that maximum speed with the information what we have. Can we apply anything energy equation here? Who does work? So if you want to just go for the work energy theorem, which is the universal applicable at all places. So initial kinetic energy plus work done by gas in the left part, work done by the gas in the right part, equal to final kinetic energy. Initial kinetic energy 0. Work done by the gas in the left part, that should be equal to minus of delta U because adiabatic process. Work done by the gas it is. I'll write it by the gas it is. So in physics, I think we are bothered about the system or we are bothered about the application of system. This is very crystal clear. Some of you previous in the last year we discussed like a physics, we are bothered about like a what I can obtain from the gas. We are not bothered about what will happen to gas. In the refrigerator you have that compressor. So when you keep any fruits, vegetables or any dairy products in the mill, in the refrigerator, what you are bothered? You are bothered about the products, no? Are you bothered about the gas in the compressor? You are not bothered about the gas in the compressor. What you can obtain from the gas from the compressor is what finally matters here. So what will happen to the gas, I'm not bothered. Altogether, okay, what is the output of the gas? So in physics, what will happen? Here, rather than on the gas, work done by the gas, something very important. In chemistry, you were more studied about the on the system. Here we are bothered about what work the system will do because that is what useful for application. I think don't bring the chemistry ideas here and totally, because here we study only first law and it's over. Chemistry you focus on second, third law, all other things. Just I think keep it your chemistry aside. It will be much easier for you here. Work done by the gas in the left part, that should be equal to change in energy, change in energy. Because in adiabatic process, what is work done by gas equal to minus delta U. Work done by extra agent, it should be okay. What is delta U? Delta U should be UF minus UL, no? So ULF minus ULI. If you know Dicey formula, you can directly jump to the formula. Negative sign I'll bring outside. No. What is ULF? Intenji in this one. So this you are going to write NR temperature. So we don't know. Again, once again, I'll just put everything. Work done by the gas equal to minus delta U. There I'm going to substitute. I'm not putting any sign for this. Work done by gas equal to minus delta U. The change in energy is going to tell us what will happen finally. The change in energy is going to tell us what will happen finally. Okay, no, I'm trying to avoid. Next part, I'll insist on. You must know what is the work done by gas. So this will be temperature here. TL, TR, we'll write it here. Okay, initial temperature, this is T1 and T2. So this will be TL nRT1 by gamma minus 1. Number of moles I think will be different. N1, N1, N2. Symbols T2 only. Okay, everything is fine. Gamma minus 1 equal to what is nRTL? nRTL should be equal to final pressure P final pressure is P, final volume is VL, minus this will be initial pressure P1, this will be V1. If you wanted, you could have directly wrote this expression VR minus P2 V2. No, what is the unknown thing? P, VL and VR. So the total volume of the gas must be conserved. So first equation, this is equation 1. Overall volume will not change, no? This is the thing. So now I need one more equation. What is one more equation? Something related. So I'll apply the adiabatic process in each chamber. So that should be equal to PL P VL gamma minus 1 is equal to P1 V1 gamma minus 1. So I know expression for P. Now gamma, helium is a monoatomic gas. So what is the value of gamma? Gamma will be 5/3. So expression for P will be P1 little bit lengthy maybe calculation, but still we can manage. Okay, similarly for the left part of the gas, PVR gamma minus 1 equal to P2 or replace for P1, replace P1 in terms of P, and I think these are the next set of equations. What I suggest is replace for VL, VL, then you will get V1, this is V2, no? V1 plus V2, it should be VL plus VR. We'll do one thing. I'll from here, I know P1 V1, I'll replace VL. Then I'll replace VR. I'll get expression for P in terms of V1 V2. That I'll substitute here. I'll get V1 and V2. So what about VL plus VR? I think that also you can replace here. I'll scroll down. I think I can simplify this. Just here, what are you to do? Replace VL in terms of P, or gamma minus 1 you send on to that side, no? So PVL you can replace with this equation. Similarly, PVR you can replace with this equation. Then you have total equation VL and VR and MVM. Anybody solve it? First we have to get expression for common pressure. Okay, I'll do one thing. I'll simplify it. Let me simplify this. So this will be VL equal to P1. Okay. Okay, fine. Temperature I took it, no? So this is adiabatic process. Only gamma will be there. Now VL, what you can write, P1 1 by gamma V1 by this will be much easier. You'll get answer very immediately. Substitute now this VL and VR in this equation. Then you are going to get expression for P as a function of V1 V2. Okay, fine. Keep it here. Okay, this one. Now what to do this one? I think you can take common VL plus VR. Again you can write V1 plus V2. I think this is not needed. I will remove it. I'll simplify here. There's one more expression is needed. Okay, this one only. Let me this will become P2 P1 V1 plus P2 V2 gamma minus 1 minus of PVL plus VR gamma minus 1. We know all these values, the left hand side bracket, and then VL plus VR, what you can write it as V1 plus V2. So this is PV1 plus V2. It will become very easy for you to simplify. Call this as equation 1. Now substitute 1 in 2 in 1, V1 plus V2. Okay, anyway it's needed. Sorry. Substitute, where is that P gone? Oh no. VR and VL substitute in this equation, then you'll get expression for P. Then that value of P substitute you'll get Vm. Okay, so this will call this as equation 3, equation 4. So put 3 and 4 in 2. Okay, you'll get that equation. Then the value of P substitute in the equation 1, you'll get the required answer. Not exactly, approximately 5 meter per second it will come. And the calculation based, I think, is more about how you take help of the basic equations. You see that the question is a little bit about how you simplify things. Okay, make observation, we'll go for it. These are very popular, some questions of this kind. Just how you apply the adiabatic equations. Everyone got the method here? Since sir, why you are doing this? Instead of all this, you should directly in exam you have to start from here. This is I wanted to write this directly. You get confused. That's why I brought from here. In adiabatic process, work done by gas equal to minus delta U. Whether gas is doing positive work or negative work, it is just equal to minus delta U. Work done by X reagent plus delta U. Go back to the work by energy chapter, gravitation chapter. Okay, that one, electrostatics. Then electromagnetism, work done by conservative force minus delta U, work done by X reagent plus delta U. Substitute here all with sign, then if the volume of gas increases, work done by gas positive, volume of gas decreases, work done by gas negative. I'll move to the next part of the question. Read this one. Very few problems we have where in thermodynamics the container will be accelerating. Hope everyone has read the question. Okay, directly I'll go for the solving of this. We have a container like this, and I'll bring a piston. The mass of container, let it be mc. Mass of piston, let it be mp. Then it is dragged by a, the cylinder, then pushed by constant horizontal force of 2.5. Pushed or pulled? Okay, okay, I'll push it here. So in which direction? Anything, either left or right. Let it be in this direction. So this is what that 2.5.
To the left, sir.
To the left. Okay, I think. Okay, fine. Yeah, it is given. No. Now what to do here now? What is the state of piston? Piston earlier was having 8 centimeter. Okay, this is without force. First, we'll have a diagram. This was 8 centimeter. Now definitely, what do we expect? The position of that has to change, no? We applied a force. So earlier this was 8 centimeter. 40, this having area of cross section A. The pressures were equal, you see that one. The pressure in each part is, okay, say we'll say earlier pressure was, say like some pressure was P. P naught will take it, not atmospheric pressure. Again, we'll do one thing, any symbol, PI, I'll write it, yeah. What will be the new position of the piston? He's asking only the new position. New position means something, some shift got there. We have to calculate this x. Sir, how? Now, who is going to push the piston? The pressure force only. So, and if container moves in this direction, at steady state, we are discussing problem. Then the piston should also move along with the container. So, therefore, the pressure on this side should be greater than the pressure on the left part. So, pressure in the right part, let it be PR, that in the left part, BL. And now all these are assume temperature to be constant, he himself is mentioning. Now what is the total mass of the system? The acceleration of system, the piston will accelerate and the container also will accelerate. Acceleration of system equal to F by mp plus mc. We know this acceleration, we know force, masses of piston, everything. Then let's come for on the piston, we'll see. This is on the system. On the piston, PRA minus PLA equal to mass of the piston into A. Substitute the value of A there. PR minus PL equal to MPF by what to do after this? Okay, till here, okay, somehow is asking the displacement of piston. What happened earlier volume? This was the initial volume. What shall we have to use symbols, no, here. V1, V2 will take it. The final volume VL and VR. The volume, shall we go for equating pressures? Temperature is constant. So shall we go for isothermal process in both the parts? No, based on that, in the left part, we'll write some equations, we'll see. Initial pressure Pi, volume V1 should be equal to final pressure PL. Volume will be Vi plus Ax. Directly let me write it. V1 into Ax. Then in the so now I can write what is PL. PL equal to P1 will write it. Yeah, P1 will take symbols P1, P2. That will be uniform. Change symbols. Initial pressure, let it be P1. So PL equal to P1 V1 by V1 plus Ax.
Sir,
Yeah.
Sir, PR minus PL into A, no sir? Area.
Volume of gas, no? PV, P1, V1 equal P2, V2. Okay, here, one area. Okay. Now, in the right part, P2, V2 equal to PR, V2 minus AX. Let me solve for PR. This will be P2, V2 by V2 minus AX. I'll substitute these values there. So what was the question asked? What will the new position, no? Okay, let's see. This is equation 1, 2, 3. So substituting 2 and 3 in 1. So PR equal to P2 V2 by now look at only what is only unknown thing. The only unknown thing is X, no? Can we solve this? Remaining all things we know it. The question is very easy if you can think it. Some students, I don't know what will happen to you. Sir, I'm very good in kinematics. then so I'll describe the motion of this with respect to this one. So initial this pressure is more than. So I think somewhere will get messed up. The maximum problem solve will be about some like a one position and final position. Intermediate, how it undergoes displacement, all we need not to bother. I think our most of the thermodynamics questions will be like that only. One initial state is there, one final state. The intermediate state, how that changes occur minutely, microscopically, you need not to bother. Especially in exam, avoid this smart thinking. When you are learning, okay. And all the processes are quasi-static. I think there's one more quasi-static we say. Quasi-static means they will occur gradual. Suddenly this piston from here to here will not come. Gradually it will shift. So what is the state of this piston? What will be the new position of the piston is telling? So from rest to rest, gradually it will shift here. Quasi-static process, all are. So you can just write it here. On paper, practically, so many parameters. There will be friction between the piston and the container. So many things will be there. The process will be always reverse. Like a irreversible will be most of the things that one. On paper, we'll just put it like a all the processes are reversible. But practical open, all the processes are irreversible. And we are assuming quasi-static, gradual, but sudden also can take place. So therefore, this word reversible, quasi-static, only on paper. I think all for 100% of numericals will be related to this conditions only, quasi-static and the reversible. Intentionally, if he brings any piston, okay, friction. If he brings no, then you can think in other way. A 2 centimeter answer. Let me simple idea based. Let's see that how you manage. So here we have the gas, that one, and this part is a conducting rod. Read the question. Now there'll be there'll be flow of, now as the piston is moved here, when this piston is shifted down, so I'm going to move it that one. Who is going to move that? The external agent. So now you go back to isothermal process. See, you should have the concept of, say, all application problems. Sir, isothermal process, temperature constant, PV equal to constant. Okay, everyone knows this. Q equal to W equal to nRT log of V2 by V1. This is just mere mathematics now. What actually happens isothermal process? Any amount of work done will be converted into heat, or any amount of heat will be converted into work done by the system. That's what isothermal. In physics, you should remember temperature constant is a definition based things, but for us the applications, what is like, what is the isothermal process? System, what do you mean by system here? The gas. So what the thermodynamic system will do, mechanical work will convert into heat, or the heat will be converted into mechanical. That's what the isothermal here. Now if I move the piston, what I am doing, I am extringent, no, I am doing work. Now I do work, then work done by extringent. So where do my energy gone? The gas will convert that into heat, and that heat will be transferred through the rod. Okay, this is, I think, the most beautiful part. Well, how piston will move? Somebody should move, no? So I am extringent, I am going to move it. Then work done by, say if you are, I think I can. If you are here, there's a piston. You move it. So your mechanical work, and let's assume that here we have connected a rod. That rod is connected here. Now whatever you do work, your mechanical energy got decreased, no? Where do it has gone? Okay, the gas will convert that mechanical work to heat, and that heat will flow through the rod. So any student who is able to think like this, I can definitely say that there is a one best engineer in you. A best engineer is residing in you. If you are thinking like PV equal to constant, Q equal to W equal to nRT log of V2 by V1, okay, some good technician is residing in you. What is the technician? What engineer tells, he will do it. If nothing is flashing, I don't want to comment further. Okay, let's get into this one. So the work done by extringent here, I need not to show much a diagram. Here I am putting it. So this is what. And the gas will convert that mechanical work to Q. Here's gas is present. So in nutshell, what is isothermal process? In isothermal process, a thermodynamic system. Who is thermodynamic system? The gas itself converts mechanical work to heat. Don't say heat energy, just leave it, call it. Heat is a form of energy, no? Heat. Or vice versa. Any limit? There's no limit. Okay, let's get into this one. So from the delta U is 0 as the gas will undergo isothermal. Temperature of gas remains constant. Because of this I'm thinking, otherwise not possible. So therefore delta U is 0. Then therefore the Q should be equal to W. I'll write it. dq equal to dw. Dw, how we write? P dv further nRT by v into dv it is asking specifically this one. So now what is dv? Dv should be equal to dq equal to nRT v a dx, change in volume. nRT a v dx by dt. What was the condition? Find the velocity of piston when it is a height L by 2. temperature constant A. What is the volume of gas will be A into L by 2. dx by dt, velocity, dq by dt. We don't know this, call h. Can you calculate h? H is this one. Any formula for h? K A temperature difference, T minus, let me write everything in symbol, substitute that here, K A T minus T naught by L equal to, that will cancel out, so 2 nRT by L into V. So we know temperature of the gas, substitute then and solve it. I think 27 only we can write it as. Not needed. Okay, no, T naught, I'll write it here. No need to convert in Kelvin scale. I do have answer for this. 5 millimeter per second. Better write. This is very important. Please, all of you, you have to please do understand the physics involved here. Don't just remember the formulas like in what happens in chemistry. We are bothered. Our application problems will be of this kind. Now, can I say like here I'll bring some air. We'll do one thing. I'll make this temperature 100 degrees. Let this be 27. In that case, what happens? The heat will flow. Then what gas will do? It will make the piston to move. Then we can calculate the piston will be start moving up. Then we can work out here. .31 joule. Right there, Kelvin. No, what is there in that one? Better go for Kelvin only. Yes, given joule per mole per Kelvin. No. Yeah, we have to write in Kelvin. 300. minus 273. This will be 273. Okay. I think it matters here. 300 here 27, here 300 will come. 27 by 300 it will be there. Check it. Let's move to the next one. Are you able to read this? I'll write down what is there. This one, a calorimeter. Let me start it. So it is having initially some 400 grams of water. At 5 degrees Celsius. To this 200 grams of water will be added. And I am going to add the ice. Ice at 10 degrees Celsius. then 400 gram of ice at minus 6. This will be added to this container. Then we'll see what will happen. Shall we do one thing? First we will, there'll be exchange of heat between these two. Then again, how to manage this? They'll add simultaneously. So first will there be exchange of heat between these two, then they'll come to some equilibrium. Then again, no, simultaneously will happen. This 400 gram will interact with this 200. This 400 gram of water, which is then calorimetry, will interact with this. This will interact with it. There'll be interaction between this content and this one. This content, this one, this content, this one. All three will interact simultaneously here. There's a very important thing. So therefore, we'll, what is the final temperature of the contents of calorimeter? Now we'll see that final temperature, let it be 0, we'll assume. Then how much of what is the energy released, that will calculate. Q naught, we don't know, just we are cross verifying things. 200 gram of water, specific heat is 1, 10 minus 0. Then 400 gram, specific heat of water is 1, 5 minus 0. 2000, 4 5 jar 20, this is also 2000. So 4000 calories is what available. Okay, for temperature. Now the temperature, it has become, this energy is available. So this energy now will be sufficient for the whole ice to melt. For all ice to melt, we'll see it. For all ice to melt. Now again I'll start with Q1. This should be equal to this Q naught, will write it. 400 gram of ice, specific heat of ice is 1. Final temperature, I'm assuming this to be 0 and minus 60. I'm just cross verifying things, nothing is there. Or we'll do one thing, Q1 will write it. So this will be 200 into 60. 12,000 calories is what needed for the temperature of the ice to make it from 0 minus 60 to 0. But how much is available? Only 4,000. So what do I expect? I think the whole ice melting not possible. First of all, the temperature of ice 0 itself will not become, no. So what is the possibility now? What do you expect the temperature? Should be less than 0, should be negative. How to calculate that negative temperature? We have to verify. So first, actually what you do is like this 600 gram, now 600 gram of water is there at 0 degrees. That 600 gram now will freeze, will become ice. Some energy will be available. Now we have 600 grams of ice at 0 degrees and 400 grams of ice at minus 60. Then again let it come to one common temperature. Again further the energy will be released here. Now there will be exchange of that and they have to come to one equilibrium. So this is all a cross check here now. So no question of this ice melting. Instead what happens, the water will freeze. Hope are you getting? Now we have to come back and we have to solve this problem. So already Q naught is there. So what we do is, yeah, we'll make it here. This is 200 gram at 10 degrees Celsius, 5 degrees. So they will combine. It will become 600 gram at 0 degrees Celsius. So then what is energy released? I have to bring energy, no? The blocks are only to make you understand. No, here some energy is released, that is Q naught will say. Then again this will get freeze. Water. See, everyone does this. Very easy to do now in exam in the 10 situation within 3 minutes. Solving this, I think, really challenging. Some again energy will be, so I'll do one thing. I'll take this as Q1. This is some, it'll be, yeah, some more. So how to calculate Q2? Q2 should be equal to 600 gram into LF. Latent heat of fusion is 80. 48,000. Again look at this. $48,000 calories are there, but how much we needed for the 12,000 is sufficient. 12,000 48,000 plus you add this one, 52,000 is available. So what to do now? I think somewhere we are in paradox, no? So all water should freeze. Some amount of water only should freeze here, not complete. Are you getting? See, like I'm telling you this one. Okay, I solved this last year. Okay, I'm making the, but first time, no, really had to verify all these things. Then I'm able to reach the answer. So the complete water need not to freeze. Only a part of water will freeze here. So from here, what do we get is like a complete. So now already 4,000 calories is available. Another 12,000 is there. To get the 12,000 calories, only some part of it will become ice. Water at 0 degrees Celsius, and other will become ice at 0 degrees Celsius. How to calculate that M1 and M2 is very important. So how much Q2 should be? Okay, this is something ruled out, no? This I'll take it out. Now we have to proceed here now. 4,000, this is available already. Another 12,000 is needed. Okay, this value is 12,000, we'll write it. I think another 8,000, sorry. Another 8,000 only. This is some small Q2, no? 8,000 is needed. For the temperature of highest from minus 60 to become 0, we need this much of energy. Already 4,000 is available. So another 8,000 is available. So how much of water should freeze? Only which will generate 8,000 calories. So we have 600 grams of water. So 8,000 come for this one. 8,000 is equal to some M1, M2 into LF 8000 m2, this is 80. So 100 grams of water freezes here. So what will be left over m1? M1 will be 500 grams, m2 will be 100 grams. So what is the final content? The final content, shall we add up? It will be 0 degrees Celsius. So how much of water? 500 grams of water and 500 grams of ice. Let me show in this way. This is the 500 grams water, 500 grams ice. Just only cross checking has to be done. You have to analyze here, nothing is there. The formulas are only Q equal to ms delta T and Q equal to mlv or mlf. Okay, make observation, I'll slide down. 2-3 problems of this kind will be sufficient. You'll get a basic idea. Then you have to proceed further to the next concept. Every day, just pick up some 20 best problems from different topics. Start thinking. Next, again on Tuesday, again on Wednesday, again on Thursday, Friday. So, in all 5 days, some 100 problems you have thought, and also you revise concept. Now, I want everyone open your page notebook and start drawing the diagram. I think by seeing we can't draw this. We have to take help of at least a little bit about the fluid mechanics. On one side we have water. What is H equal to 1.8? Temperature of water is 40 degrees Celsius. Now I think you take help of this. Height of the is 1.8 meter is there, and let the whole water, whole ice, let it freeze. So is it this temperature of water sufficient for the whole ice to freeze? There's the one primary question. So for that we have, so what is the mass of ice? What is the mass of ice present here? We have to calculate. So let A be the area of cross section. Sir, area of cross section not given. Look at that, also not available. But that A will get cancelled out either way. So what is the mass of water? You calculate here, because you know H. This H is there. Initial mass of the water, let it be M1. Initial mass of the is M2. Then M1 should be equal to density of water into area into H. Specific heat of water 1, 40 minus 0. I think I'll proceed in this way. This will be M1S. There's only cross check. I'll do that cross check. M1 specific heat of water 40 minus 0 equal to M2 specific heat of ice. Oh, sorry, this should be LF. M1 should be density of water. AH, this will be 1, 40. M2 should be equal to density of ice, AH into 80. Okay, I think it's not equal, no? You can see this. What all heat that is available here is not equal to. I'm just using some simple basics here. What is the density of water? 1000. Density of this is 800. You check it now. Definitely this 1000 is in fact less than this value. So therefore all ice will not melt. Okay, now we are in better position. Then only some part of ice will melt. So how to calculate what is the part of ice that will melt? So we'll take help of this. M1 specific heat of water 40 minus 0 equal to some amount of ice that melted, M into LF. This will become density of water AH specific heat of water into 40 mass of ice that melted. Shall we? Okay, we'll do one thing. Some mass. This also we can write it as density of ice, area, some x length of ice melted. Anybody value of x? One meter, huh? Yeah, okay, 1 meter. 1.8 meter was the height of the ice column, of which 1 meter will melt. Then how much length of water column it will make it? I think the densities are different here. What length? Because the area of cross section is same, no? So therefore here I'll go for density of ice A into X should be equal to density of water A into Y. What length of water column it will produce when X length of ice column. So this is the length of ice column melts. What is Y? The length of water column that is produced. This one. So the density of ice, this will be 800. X is 1000. This is Y. So Y is equal to 0.8 meter. What I should call? Length of water column produce due to melting of ice. Okay, already we have continued. What to do there? Now we do that 1 meter of ice melts, then what do we get? 0.8 meter of the water column will get it here. Calculate the height of water in container B. This what the final thing is what being asked. What to do with this after this? Level of water is asking, no? So how much of water will go on this side, how much of water will stay here? We don't know that. Am I right? Some y length of water is formed here. will it stay here only? No, some part of water will go there, and this level of water will rise. So finally, what do we get? We get a situation of like this. How to proceed after this? So this ice is, some ice got melted. Some water will be present here. And what is the temperature of water now? 0 degrees Celsius. The level of water, it will rise. Already it was having h height, so some level of water will rise it here. Now what is volume of water will be? Earlier it was like volume of water will be HA, will be, now it will be HA plus YA. This will be 0, this value we know it. I'll write it. What shall I write here? Volume of water is H plus Y. That L should be equal to Y. No. This Y length of water column, in that sum L1 I'll write it, sorry, L1 water, ice, water, 0 degrees Celsius, 0 degrees Celsius. Okay, I'm able to write this much here. Now come for this one. The pressure at this point should be equal to pressure at this point, or we'll write some other thing, C and D. A, B already we have chosen, no? 1 and 2. Because they are in equilibrium, so pressure at 1 should be equal to pressure at 2. What is the pressure at 1? Density of ice G into 0.8 plus density of water G into L1, density of water G into H plus L2. What is L1 plus L2? Should be equal to Y, no? Two equations I'll get it. Solving this I'll get L1 plus L2 one value. Here L1 plus L2 should be equal to Y. Or AL1 plus AL2 should be equal to AY. It is. Solving this we'll get expression for L1 and L2. Then I can H plus L2 is what our answer. Somebody should work out here. Okay, now you see the calorimetry applications, mixed ideas. All these are some time needed, some 5-6 minutes I think needed, not even 3 minutes, not possible, because reading only question only 1.5 minutes it will take it. Again drawing diagram, analyzing. So mostly in passages they may break up, they'll ask you. I have answer, we'll take the next question, sir, because 12:30 it is. H plus L2 is cross verify afterwards. Read the question. There's a gas is present. Read the question, I'll just shade it. All this one. Yeah, I'll finish off this. Read the question, meanwhile I'll set the diagram, because you feel that empty. So this is a gas. 1.52. You have to, I'll 1.52 not 1.71 everyone 1.52 confirmed. I'll change it. Density of ice and water are different, I think, carefully. .9 he has given density of ice. Read this question. Hurry up, this little bit lengthy. Check calculation, maybe. What is a thermostat? I think thermos flask. You might have seen thermos flask. So what it does, the temperature of the liquid filled up inside will remain constant. Here thermostat, what it does is like, it will, what all the excess heat which is generated here, it will absorb it, so that the temperature of the gas in the left part will remain constant. Now a Q amount of heat will be supplied here. Then we have a springs, then we have a piston. So after supplying heat, what actually goes on supplying it, what actually happens, that we'll see it. Okay, this particular piston will get shifted up. We'll have like this. So the pressure here, so the temperature of this gas, let it be delta, it will rise. The temperature in the left part will not change because the thermostat is there, though like it will absorb some heat, and because of that Q, I'll put it. So that Q is what we have to find out here. Determine the heat Q given away at the temperature T to the thermostat by the left part of the piston. Okay, there's a piston. We'll have some. Okay, of course it's a massless is telling. Not needed, no? Yeah, why to? Yeah. No, what actually happens with the pressure? The pressures will be different. Here the pressure, let it be PA. Here the pressure will be P dash. And the spring got compressed, so it got shifted. So this will become L by 2. Total length of cylinder is how much? 2L, no? Yeah. This will be L minus X. It will shifted by X equal to L by 2. Okay, I have to write L by 2. Then how much it will become? L by 2. This will become 3L by 2. Now what all the data given first will analyze. So time being, let me write X. And what is X? X equal to L by 2. Now what is the state of this spring? Both the springs are compressed, so the spring force together 2kx, where in fact X is equal to L by 2. P1, P2 will take it. Symbols, it will be easy. At equilibrium. At equilibrium, what is the equation we can write? No. Okay, sir. What is the thermodynamic process it is going on? We supplied heat. The temperature of the gas in the right part will increase. At the same time, the gas will also expand. This gas in the right part will push the piston. So therefore, the gas in the right part does positive work. The gas in the left part does negative work. Spring forces also doing work. So how to bring all? So heat is supplied. Some mechanical work done by the gas is present, and also there's a rise in temperature of the gas in the right part. There's no change in the temperature of the left gas, so intensity of the gas in the right part will increase, that in the left part remains same. Then the work done by the gas, and there's also work done by spring force, so we have to bring all this, and also heat will be absorbed here. So what all the heat supplied, so Q is equal to work done by gas in both parts plus change in internal energy in right part plus heat absorbed by thermostat in left part. Now this will be very, you can straight away start objecting, sir, you're not bringing spring force, you're not at all bringing the spring force CV, changing temperature delta T, this is Q. Straight away, sir, work done by the gas, what about the spring force, work done by spring force, why you're not bringing? All of you 2K, okay, no, because both they are in series. How much this will elongate, that much this will complete. So 2kx I'm writing. So why you're not bringing the work done by spring force? Let's see that. What will happen to this pressure force, P1A, P2A, and 2kx? All these three forces are doing work. What will happen to that? That I'll see that one. So the thermodynamic equation is what I am writing. The first law of thermodynamics is what we have now. That is what I presented. Now let's look at the at equilibrium. So this will be P2A sorry, P1A minus P2A minus Kx equals 0. How do this? There's a quasi-static process, no? As you supply it gradually, the piston will be shifted gradually, not from like it will accelerate. From rest to rest, it will move. And finally, it will come to this particular position. 2kx. Yeah. At equilibrium, finally, no. The gas in the right part does positive work. The gas in the left part does the work. Okay, what is work done by the gas? We have to put it. So now work done by the gas is equal to dW1 plus dW2. What is dW1? P1A dx. P1A dx minus P2A dx. So this will become P1 minus P2A into dx. The sum of that one. So P1 minus P2A. This will, everything will become 2kx dx. How I am bringing this equation is very, very important. So this will become k x square. What is x? X value we know. X equal to L by 2. Everyone is welcome to oppose this. So spring force will do work or not? Yes. Gas in the right part does work or not? Yes. The gas in the left part does work or not? Yes. Then why you are writing like this? Okay, you have to go back to the thermodynamics. What is the work done by the gas? Work done by mechanical work done by the gas. It should be reflected somewhere in the system. No? The gas does mechanical work, and what you see, either there'll be increase in kinetic energy of piston, or some spring should be compressed. This will be totally against little bit of your chemistry. Here, work done by the gas is here mechanical work. It is called better mechanical work done by the gas rather than saying work done by gas. Better say mechanical work done. Means the gas does work. How it will be reflected? It should be reflected into some mechanical energy of system. Who is there? Either the kinetic energy of piston or the spring should accept, or the increase in gravitational potential. Something should happen. So the gas does work. The work done by the gas is nothing but equal to increase in elastic potential of spring. If you remove the springs, okay, then see, sir, what will happen? Okay, sir, springs are there. Okay, you remove spring. Then nobody is there to accept, means work done by gas is zero. It will become like a free expansion. So always open mechanical work done by the gas. There should be an agent who should be in a position to accept it. Who is that agent now? Extra agent is the spring. The spring is what going to accept that energy. Now, this is, I think, very core essential of our thermodynamics here. The first law of thermodynamics is what? Q equal to delta U plus W, or W gas. What is that work done? Mechanical work done by gas, you call it. Better don't call work done or work done by the gas. Mechanical work done by gas. There should be some extra agent who should able to accept that work. If there is no extra agent, no, it will become just like a free expansion. Okay, I got now work done by the gas here. Q is what given. Somehow the change in temperature is needed. Change in temperature in the right part. How to bring that one? Shall we take help of number of moles? Again, I'll take help of the same equation only. At equilibrium, P1A. There's a very basic fundamental thing is what being reflected. What is P1? Pressure is P1. P1 should be equal to pressure in the P1 what we took on the right side of, no? Okay, I'll keep this diagram, I'll write it. I'll shift it down. We'll write the same equation. Looking at this, P1A minus P2A minus 2kx equal. What is P1? P1 will be N R T plus delta T by A into L plus L by 2. What about P2? P2 should be equal to N R. Temperature will remain same, no? The temperature will not change, by A into L minus L by 2 minus 2k. X is how much? L by 2. All set equal to 0. I think solving this, I'll get the delta T. What is NR? Still we don't know NR. N is number of moles are given. Will equate next one more step. T plus delta T. This will be 3L by 2, no? 3L by 2 Okay, I think solving will get expression for delta t. 3k L square. This is delta. Substitute that there, we'll get the expression for q. I think this is a very primary equation. No? We may take it lightly because at equilibrium, the whole concept just revolving around this one only. A will be there. A must be there. Yeah. Delta t is there. Here. Only for this. Okay, only for that it will. 3a, I'll write it. Once again, okay, the last part, the work done by gas is something very important. This is once again I'm repeating. The gas does work. What all work done by gas, where do it has gone? The gas in both the parts does work. That affect what you can see, change in elastic potential of spring. A gets cancelled. Huh? One A is there here, no? I'll remove this A, sorry. Yeah, P1A we have substituted, no? Let it be here. Or else you write A and here A and cancel out. Better. Okay, fine. Now. Once again, anybody having doubt, please clarify the very essential part. Our entire first of thermodynamics work done by gas, meaning is what I'm trying to bring it here. There should be some agent who should receive this work done by the gas. A little bit some lengthy questions I picked up. Okay, I'll end up the class. Yeah. Okay, kids, like we had a discussion on some application problems on calorimetry. Then we took some thermodynamics, some problems related to that. So in coming class, we'll explore few more numericals related to this. Meanwhile, you have to put effort in recollection all the data. Then you have to work out numericals. Okay, thank you all of you.